Hi everyone, welcome to this presentation about reducing the energy consumption of software product lines. I am Edouard Guegain and I work on this subject with Clément Quinton and Romain Rouvoy. Along the last decade, several studies showed that software has a significant impact on the overall energy consumption. Green computing has emerged as a way to mitigate this impact. Green computing focuses on two different tasks. The first one is measuring energy consumption of software, and the second one is mitigating energy consumption. Measuring the energy consumption of a software is already a challenging task, but in software product lines, the variability creates an additional level of complexity. So, what are our goals? We want to identify the energy consumption of each feature from an SPL without looking at the code, because the number of features and the size of each feature can be very high, and without measuring each product, as the number of valid products can also be very high. Our goal is to create energy-efficient products by using energy-efficient features. In order to illustrate our methodology and our experiments, let me introduce Robocode and Robocode SPL. Robocode is an engine in which community-developed robots fight each other to identify the strongest one. The robots are autonomous during battles, so the strongest robot is the one with the best algorithm and strategies. In this video, you can see two robots fighting. They are able to move, to aim, to shoot, and in blue you can see their radar. A match ends when only one robot survives. Robocode SPL is a product line designed to create robots for Robocode. In this SPL, there are 5 main features: radar, targeting, movement, select enemy, and gun. For each of these features, an implementation must be selected. There are also 3 optional features related to resource management of robots. That's a total of 72 concrete features, which can be composed into 1.3 million different robots. For our experimental setup, we sampled products from Robocode SPL in order to have a set of random products. Each of these random products were measured in a specific context. We want to minimize the energy consumption of matches against a specific opponent, so we created a match between each random robot and this fixed opponent. The energy consumption of Robocode was measured during each match in a way that excludes the energy consumption of the startup and shutdown of Robocode. The idle energy consumption of the system was also removed in order to minimize noise, and the matches were performed in command line to avoid noise from the UI. To consolidate our data, each product was measured several times. We analyzed this dataset with 2 different analysis methods, one focusing on individual features and one with regard to feature interactions. The remainder of this presentation will compare these 2 different approaches. Now that we have the energy consumption of random products, how can we detect the performance of features? To do that, we create a matrix with as many rows as there are products and as many columns as there are features. The elements of the matrix are the energy consumption of the corresponding products if it contains the corresponding feature. For instance, in E2N, we will report the energy consumption of the product P2 if P2 contains the feature Fn. Otherwise, we let the cell empty. Computing the median of each column gives us the median energy consumption of the products containing each feature. It is then possible to compare features with each other. A quick example. let's say that a product line has three features, A, B, and C. The product P1 has an energy consumption of 3 joules, and it contains the features A and B, so we report 3 in the corresponding cell. Same thing for products 2 and 3, and at the end we can see that the products containing A consume less than B or C. Now, let's take a look at some features from Robocode SPL. In this diagram, you can see each movement feature, named from M1 to M26. The vertical axis is the energy consumption in joules, so lower is better. Each box plot represents the energy consumption of the products which contain the corresponding feature. For instance, the products containing M1 have a median energy consumption of 6.5 joules. Our analysis method focuses on the median energy consumption, so here there are 3 obvious best features, M6, M7 and M8. The best one is M7 with a small advantage. There are also some obvious bad features, such as M1, M20 or M26, among others. We don't want such features in our products. Here is a similar diagram, but this time with the different targeting features, T1 to T23. There is less spread between the features. T4, T6, T7 or T17 have higher energy consumption, and the best feature is T8 with a small advantage. Using this data, the strategy to reduce energy consumption of products is straightforward. The best product is the one composed of the best feature from each group, the best targeting feature, the best movement feature, and so on. We will call this product BT0 for best product in theory. If a stakeholder asks us to improve his products, but specifically ask for a feature, path equal movement for instance, that's not a problem. We just replace all other features with the best option available. So we have a product BT0, which is, in theory, the best product. Let's check how it performs. The first box plot is BT0. We use random products to measure the energy consumption of features. So as a reference, you can see here the median energy consumption of each of these products. Each of these points is a median, and this box plot shows the repartitions of these medians. As you can see, a lot of random products outperform this supposedly best product. In fact, BT0 performs better than barely half of them, so we must be missing something. The product composed of the best features is not the best product due to feature interactions. Features interact with each other. These interactions can be at code level, for instance, method call between different features. But interactions can also happen at behavior level, and features can collaborate or obstruct each other during the execution of a task. In software product lines, these interactions mainly happen between pairs of features. To take such interactions into account, we create a new matrix. And instead of having one feature per column, we have one pair of features per column. An example with the feature A, B, and C. We have the pair AB, BC, and AC, and the median of each column gives the relative energy consumption of the pair of features. Earlier, I showed the energy consumption of each targeting feature. You can see them again in the graphic at the top. Here you can see the rank of these features. T8 is first with the lowest energy consumption, and T6 is last, 23rd, with the worst energy consumption. In the movement features, M7 was the best feature. So let's compare how the targeting features evolve when paired with M7. You can see that the overall consumption is lower because M7 is efficient. But most importantly, the rank of targeting features are changed. For instance, T13 is the best targeting feature when paired with M7, but in the feature-wise analysis, it had the rank of 19, one of the worst. This can explain why the product composed of the best features is not that efficient. With this method, we have a graph with the features as nodes and energy consumption on the edges. Improving a product is more challenging, as we can't just replace bad features with better ones. We introduce a scoring system for features to identify which one must be removed first in a specific product. This score is the interaction score. For a feature F, it is the sum of the consumption of each pair of features containing F in the product to improve. So let's say that you want to improve this product P. For the feature S1, in this specific product, the interaction score is 2.5 plus 2.07 plus 3.09 plus 2.4 for a total of 10.06. We compute the interaction score of each feature in the product. Now we will perform several iterations of an algorithm. The first feature to change is the one with the highest interaction score. In this product, it is S1, which is a select enemy feature. However, the feature model requires that a select enemy feature is present, so a replacement must be identified. So we compute the interaction score of all select enemy features, and we replace S1 with S3, which has the lowest interaction score. In the event that S1 already had the lowest interaction score, we just proceed to the next feature in order of interaction score, which will be T1 in this example. Now we have a new product with S3 instead of S1, so we can proceed to the next iteration. As we change the feature, all interaction score must be computed again. Now the worst feature is G1, which should be replaced. For the sake of the example, let's say that the stakeholders requires that G1 remain in the product. That's not a problem, we can accommodate this choice. As the consumptions are on the edges of the graph, we can change the other features to improve interactions. We can't remove G1, so we proceed to the next feature by interaction score, which is T1, a targeting feature. Again, we compare the interaction score of each targeting feature to identify the best one. And we create a new product, P2, with the best replacement option for T1. We will keep performing these iterations until all the features are either required by the stakeholder, like G1, or the best option among all substitution options. At the end, we compare the products resulting from each iteration, P, P1, P2, and we use the one with the lowest energy consumption. Now, let's apply this algorithm on a use case. The first approach, the feature-wise approach, converges toward a specific product, BT0. This product was not very efficient compared to random products. Now we will apply the pairwise approach on BT0. The algorithm performed 3 iterations. BT1 and BT2 were gradual improvements, and BT3 performed slightly worse than BT2. Thus, we will use BT2 as a result of the pairwise approach. BT2 is 30% better than BT0, which is a significant improvement. BT2 outperforms a lot more random products than BT0. But if a few random products are still more efficient, why can't we use them? There is a simple reason to that. Stakeholders have requirements, so they have required features. The random products may not contain these features. Let's take a look at what happens for products with requirements. We generated a set of 500 random products, and in each of these products we defined one random feature as a requirement, which can be removed. We applied both approaches on these products. Here are the results. On the horizontal axis, you can see the energy consumption of the products before improvement, so the random products, ranging from 1.8 to 12 joules. On the vertical axis, you can see the consumption of the products resulting from each approach. The feature-wise approach is in red, and the pairwise approach in blue. The resulting products range from 1.8 to 3 joules. Overall, the products resulting from the pairwise approach have lower energy consumption than the products resulting from the feature-wise approach. You can also notice that the final energy consumptions are constant for both approaches. They are independent from the initial energy consumption. In order to look more precisely at the difference between the two approaches, you can see on this violin plot the energetic gain or energetic reduction of each approach. For the feature-wise approach, you can see that the whole quartile is at 0, as this approach only improved 72% of products. The median gain is 20%. For the pairwise approach, 96% of products were improved, and the median gain is 40%. This means that the pairwise approach improved half of all the products by 40%, whereas the feature-wise approach had such gain on only a quarter of the products. Thus, both approaches are able to improve products with requirements, but the pairwise approach, which takes feature interactions into account, leads to better energy savings. So a quick recap. We used the sampling-based analysis method, and we used the resulting data to improve products. However, feature interactions impact performances. When we take feature interactions into account, we can improve more products, and these improvements lead to higher gains. So in the end, feature interactions can be used to reduce energy consumption. Now, we plan to apply this approach on other use cases, such as virtualization in data centers. Thank you all for your attention, and also thanks to the team of SPLC 21 for organizing this event.